Next, we'll discuss another type of series, telescoping series. It is also nice because it also has nice properties that allow us to find the limit with not so much effort, I guess. So let's get started. Telescoping series, and it's really hard to describe in general what it looks like. So instead, let's consider an example of the following series. And this series is an infinite sum of infinitely many terms, and we can try and find each of these terms by plugging in n into the formula. So a1 will be 1/6, a2 will be 1/12, a3 will be 1/20, and so on. And if we are going to look at the series as the sum of these fractions, then we're not going to be able to see the pattern. So in order for us to see the pattern, we actually have to see deeper, and we have to notice that 1/6 can be expressed as 1/2 times 3, and it can be expressed as a difference of these two fractions. Similarly, 1/12 can be expressed as a difference, and you may guess as the difference of what two fractions. Yes, it will be 1/3 minus 1/4. 1/20 can be expressed as the difference of 1/4 and 1/5, and 1/30 can be expressed as a difference of 1/5 and 1/6. So you may say, so what? How does this help us? Well, let's write it all out carefully. So instead of a1, so we're going to continue writing out this sum. Instead of a1, we're going to write 1/2 minus 1/3. Instead of 1/12, we're going to write 1/3 minus 1/4. Instead of 1/20, we're going to write 1/4 minus 1/5, and so on. And you bet we're going to have somewhere down the line, we're going to have 1/999 minus 1/1000, and then right after we're going to have 1/1000 minus 1/1001. And what do we notice here? We notice that if you get rid of all the parentheses, well, since we don't need them anyway, we can group the terms. And what do you see? The 1/3 and 1/3 cancel each other, 1/4 and 1/4 cancel each other, 1/5, and you bet there will be 1/5 somewhere there, cancel each other. This 1/999 cancels with the previous one of the 1/999, and 1000 cancel with this, and so on. So what happened is that this entire series literally collapsed, or we call it telescoped, into something like this, 1/2, and everything seemed to cancel except the very last term. But by the nature of the last term, the fact that it's 1 over some large number, it goes to 0. So after everything telescoped and the remainder is approaching to 0, we can conclude that this entire telescoping series converges to 1/2. Now, how do we explain this behavior using, I guess, some reasoning other than observing patterns? So what just happened is that we noticed that this series can be rewritten like this. So using the partial fraction decompositions, we can rewrite a fraction inside into a difference of two fractions like this. And what does that mean? That means if we consider the kth partial sum, the kth partial sum will be equal to this. So S3 will be 1. If we add 1/4 here and then subtract 1/5, and 1/4 will cancel each other, and we're going to end up with just 1/2 minus 1/5. And we can speculate here. Well, it's not much of a speculation, it's just we can observe the following pattern. The kth partial sum will be equal to 1/2 minus 1 over k plus 2. And what does that mean? That means we just obtained a formula for the sequence of partial sums, meaning that we can find the limit of a series by simply considering the limit of this sequence. But this is a relatively easy limit. 1 over k plus 2 approaches to 0, and we are left with 1/2. So this is how we know that this series has the limit 1/2. Now, each of these telescoping patterns is not unique, but there are only few of them that you should learn to recognize. So one is with fractions, and here's another one when logs are used. And you may say, like, well, how exactly this is going to telescope? We have ln of 1/2 plus ln of 2/3 plus ln of 3/4, etc. How exactly is it going to telescope? Well, recall the property of logs. In fact, recall that ln of a over b is the same as ln of a minus ln of b. So what does that mean? If we continue writing this sum, that means, well, I guess instead let's consider the kth partial sum. So we're going to have ln of 1/2 plus ln of 2/3 plus and so on, and we're going to have ln of k over k plus 1. Now, using the property of logs, we can write it as ln of 1 minus ln of 2 plus ln of 2 minus ln of 3, and so on. And at the end, we're going to have ln of k minus ln of k plus 1. So in this case, what we notice here is that ln's of 2's and 3's and k are all gone. Ln of 1 is equal to 0, but we still have the term ln of k plus 1 left over there. So when we find the limit of this partial sum as k goes to infinity, we're going to end up with the limit of the negative ln k plus 1, but we do know that as k goes to infinity, ln of infinity is also infinity. So the final answer here is negative infinity, and therefore the conclusion is that this particular series diverges. We were able to prove that by identifying this telescoping pattern. So one remark I want to make here is that the telescoping, along with geometric series, types of series for which we can find the sum. So what does that mean? Well, a little hint. If the problem says on the homework, find the sum, well, the only series that we can find the sum for are the geometric or telescoping. So if the problem says find the sum, the series that you're working with, it's either geometric or telescoping. So this concludes the introduction to telescoping series. The only thing that you need to know here is that there are a few distinct patterns that you should be able to identify and perform this process of telescoping, meaning finding the expression for the partial sum and then finding its limit.